grade 11 Mindsetters, welcome to your physical sciences show. I am Looney and with me today is TK.
Yes,
How are you,
right.
TK?
I'm good. How are you, Lini?
I'm good, thank you. It's been a
Yes.
while, hey? Haven't
It's been
seen
some
you in
time. I've been
ages.
trying to check where is Luni.
Yeah, I haven't been here in
And
a while on a
here
Tuesday.
you are. Good
So
to
what are
see
we
you.
doing for the grade 11s today?
Well, today we're going to deal with mole calculations. We'll be looking at mole calculations from gas point of view. We'll be looking at mole calculations from the mass and molar mass point of view. So it's a lot of things that we want to bring together because sometimes learners think these things are loose and different. So we're going to be bringing most of those things together. Okay, now let's just make a start here. Now,
Before you start, TK,
yeah.
I just need to tell them how to get a hold of us.
All right, good.
Mindsetters
Yes.
on Facebook. You can get a hold of us on facebook.com/learnextra. And then on Twitter, our handle is @learnextra. And then to get all the show notes, the videos, and the schedules, you go to learn.mindset.co.za. And the website is pretty friendly now for all smartphones and all feature phones and for every computer and all of that. So you go to our website. And if you want to win this awesome Casio calculator, all you need to do is go to the link on our Facebook page for the Test Yourself competition for grade 11s, and then you fill in all your details, you answer all the questions, click on submit, and then you'll stand a chance to win this awesome Casio calculator. Entries close Friday at 12 in the afternoon. TK.
Good. Thank you, Luni.
All right.
Now let's take it. Like I said, we're going to talk a lot around the concept of a mole. So we're talking mole a lot today. We're going to discuss mole calculations from all angles, from gases, solutions, and of course in reactions. We'll also consider information given in a balanced equation, but not so much of that, but we will obviously be looking at, and just for your information, this lesson will be followed by another one that talks more to it. So all these things will tie up and come together at the end of the next lesson, and we obviously going to solve problems relating to mole ratios in gases and solutions. So that's what we'll be doing in this lesson here. Now, here is the challenge question for the day, all right? And I just hope that I get many of you getting it right. Sit down, take it down, work on it, see if you can get it right. I'll be so happy if 100% of you get it right. Your teacher in class has requested you to prepare a standard solution. Standard solution. This solution is a solution of sodium hydroxide, so it's a base. You need to revise these kind of things. Sodium hydroxide is a base. All right. This solution must have a concentration of 0.5 mole per cubic decimeter. Find the mass. So the question is, find the mass of sodium hydroxide that you will need to prepare this solution. Okay. If you're going to use this volume here, 200 cubic centimeters. Okay, so that is the kind of volumetric flux that you're going to use to prepare that solution. Work out the exact mass of sodium hydroxide that you're going to measure in your lab and work out or prepare that solution. And of course, you can use it as your standard solution for your titration processes. Okay, good. That's a good one. Good luck with it. Let's move on. Right, now, when we talk of moles, and especially when we're talking around gases, okay, what is a mole? A mole is just an amount of matter. It's the substance, it's this amount of matter that constitute a specific value. And that amount, we can call it a mole. And remember that if we have this, the Avogadro's number of particles of anything, Avogadro's number, all right? Then we have a mole. Those particles should be 6.02 by 10 to the 23 particles, whether we've got molecules of a gas or whatever. If it amounts to that number, we've got a mole. So it is just an amount of matter. Mass, when we deal with masses, when we are given mass from a particular situation and we are to find moles from mass, if we are to find moles, we use this very important formula. That number of moles is equal to given mass divided by the molar mass of the substance. Okay, that M there is molar mass. We know that from here, what small n represents is the number of moles, which is what we will be looking for. And what small m represents, it's the mass of the sample. In other words, if you are given a substance in mass, grams, kilograms, whatsoever, for you to get the number of moles, you use this formula. So m is the given mass of that sample or that substance. And capital letter M with a small letter, with a subscript m sometimes, or just capital letter M, that is what we call the molar mass. It's the molar mass of that substance. And this you get by working it out from the periodic table, okay? And its unit of measurement, it's grams per mole, right? So we know that. Next, when we're talking moles, and this time talking about gases specifically, we know that from gases, when we talk of volume, there is a volume that is occupied by 1 mole of a gas at standard temperature and pressure, which is this here. And that volume is 22.4 cubic decimeters. Let me just explain this a little bit, because I think some people sort of get it confused with it. Look, what we are saying with standard values, the volume that can be occupied by 1 mole of a gas. If I've got 1 mole of a gas, say nitrogen dioxide, 1 mole of nitrogen dioxide at STP will occupy 22.4 cubic decimeters of volume. So if I've got more than that, the volume will be slightly more according to the amount of gas that I have. If I have got a little bit less, the volume will also be a little bit less, okay, less than 1 mole. Why? Because only 1 mole will occupy 22.4. If it's less, then there shall be a lesser volume. Okay, good. So if we're talking about that situation, it would mean that this number of moles, N, the very same N, will be given by the given volume, okay, divided by the molar volume. And what do we mean by the molar volume? We mean that 22.4 cubic decimeters. Again, N is the number of moles, V is the given volume of the sample of a gas, and Vm, or V subscript M, is our molar volume, which is 22.4 cubic decimeters per mole. Okay. Now, if you were to convert then, converting from, say, because we know that we don't work in cubic centimeters, but usually our volume is given in cubic centimeters, okay? And sometimes in cubic meters. And sometimes, of course, we are required to move from these values to cubic meters. So how do we convert? If I am in cubic decimeters, 1 cubic decimeter equals 1,000 cubic centimeters. And 1 cubic meter is 1,000 cubic decimeters in that way. So that would mean that if I am to move from cubic centimeters to cubic meters, then I'll have to multiply by a factor of 10, to the power minus 6. In other words, dividing by 1,000,000. Okay, so that's what it means there. In a balanced chemical equation, the number in front of the chemical symbols will always describe the mole ratio of the reactants and products. Okay, simple. If you have this example here, for example, if I've got H2 gas reacting with O2 gas, giving me H2O gas. All right, this is vapor. If I balance this equation here, I'll put a 2 there, and that's a 4, so I will therefore have a 2 here. What we are talking about is this. These numbers are the ratios in which The reactants here are combining to give us the products here. Okay. Okay, and the ratio of hydrogen, for example, to water, it's always 2:2, therefore it's 1:1. But for oxygen here, the ratio will be 1:2, all right? So it will be 1:2. That is the ratio that we're talking about when we're talking about the number in front of every substance there, giving us the ratio in which products or in which reactants and products are actually related to each other. Okay, now, when we talk of concentration, what is this? We can have moles in solution, okay? So in this time we take moles of substances, we dissolve them in solution. When we do that, we create or we form something called a concentration. The concentration of a solution refers to the number of moles of dissolved substance per unit volume of that solution, which is of course in cubic decimeters. A solution of known concentration, we call that a standard solution. The concentration of a solution is calculated using the following formula. Okay, now that becomes very important. So concentration equals number of moles divided by the volume in which this number of moles or this amount of a substance has been dissolved. Okay, so we should know that our C there stands for concentration, and it is measured in mole per cubic decimeters, small letter n, number of moles, and V there, the volume in which this number of moles have been dissolved. Okay, so that is what it is all about there. Okay, so you would see here, if I were to look, we're talking a lot around moles here. Let me just use this part here to link up something. Mole. We saw that from the mass, given mass, okay, number of moles will be equal to given mass over molar volume, okay, for the molar volume. Okay, so there we go. But the same mole, we also saw that if I'm talking about gases at STP, the number of moles can be found by looking at the given volume divided by the molar volume, which is, of course, always, remember, this is always 22,4 moles per cubic decimeter. Okay, moles per cubic decimeter. Okay, so that is the molar volume. But then the same mole, okay, the same mole, when we're talking about concentrations, what happens? We see that concentration is number of moles over volume. Very important. But then if I were to just talk, talking about number of moles from this equation here, number of moles will be equal to concentration times the volume. This is when we're talking solutions. So all this becomes very important for you to note because they are related. I mean, if we're talking about an amount of a substance, a specific substance, whether it's a gas or whether it's a solid substance, whether it's a liquid substance, if we're talking number of moles, that N applies here, and it will also apply when we're talking concentration of that substance. It will apply when we're talking the mass of that substance. It may not apply if we're talking about gases, if it can never, convert into being a gas. But if we heat it, to high a temperature enough, we know that it can vaporize. Okay, so all these apply. In other words, when you're solving problems that involve moles, think about any possible way of working out those solutions. Okay, so I want to leave you at that point. And when we come back, obviously we're going to look at some questions and see how to answer questions based on what we are doing today.
All right.
Loni.
Okay. Mindsetters, let's take a very quick break. Don't go anywhere. We'll see you straight after this. Welcome back, Mindsetters. From that break, a quick congratulations goes out to Tabongosi. You have won yourself this Casio calculator. Well done to you. Thank you so much for entering the Taste Yourself competition. And Mindsetters, if you want to win this calculator, it's simple. Taste Yourself questions are on our notes, and the link to the Taste Yourself competition is on our wall, on our Facebook page. You click on the link, it is working. You open it up, it's a Google document. You fill in all your information. You click the submit button and you'll stand a chance to win this Casio calculator. TK.
Good. Thank you, Loni. And congratulations to
Tabo.
To Tabo Nkosi for winning that Casio calculator. It's a very useful tool for any physical sciences, mathematics learner. So I hope you're going to use it quite fruitfully in your studies. Now let's come to these questions here. We are going to see how you are supposed to answer them. Question number 1 here says, a certain mass of nitrogen gas, or nitrogen dioxide gas actually, so we're talking NO2. This gas occupies a volume of 350 cubic centimeters at STP. Calculate the mass of the nitrogen dioxide gas that is present there. Now we are given this here, we're given the volume that is occupied by the gas. All right, we have the volume. We are also given the type of the gas. We are also told that this gas is at STP. Okay, now if it is at STP, what do we know? All right, what do we know? What we know is that 1 mole of this gas will occupy 1 mole of this gas will occupy 22.4 cubic decimeters of volume. So the question is, how many moles of this gas will be occupying this volume here of 350 cubic centimeters? And of course, we will need to convert it into cubic decimeters. So let's just do that immediately. So this is equal to 0.35 cubic decimeters. So that's when you have converted cubic centimeters to cubic decimeters by dividing by 1,000 here, so that you get to the cubic decimeters. Okay. Now, how does this help us? We are to find the mass of nitrogen dioxide in that container. But then how do we get there? We need to start by finding the number of moles in that volume. And the number of moles in that volume will be, all right, so because we know the molar volume, okay, we know the molar volume, the volume occupied by 1 mole of that, and we know the volume that is occupied, the exact volume occupied by this gas. We can then say number of moles of the gas available. Okay, you can say N will be found by given volume divided by the molar volume. Now, given volume is 0.35 divided by the molar volume is 22.4 moles per cubic decimeter. Okay, now, so what will this work out to be? Right, you can use your calculator quickly. right? So let's go to the calculator. It's 0.25 or 0.35. Oh, delete. 0.35 divided by 22.4. 22.4. All right, so what will this work out to be? Right, so that is 0.016 moles. Okay, so 0.016 moles. Okay. All right. So if this is zero, we've got 0.06 moles of what? Remember, of nitrogen dioxide. The question wants us to find the mass of nitrogen dioxide in that container. Now, this means that we can actually say, because from this formula, number of moles, oh, what's going on with this thing here? Right. Number of moles, N, is also given by mass divided by molar mass. Okay. Now, the question is now, do we have the molar mass? We don't have the molar mass. We have to work it out. Okay. So there should be a way of us finding out what that molar mass is. And how do we do it? This is the molar mass of nitrogen dioxide. So molar mass of nitrogen dioxide, we can find it out, MnO2, molar mass of nitrogen dioxide. How do we do that? We go to the periodic table. For nitrogen, let's check it. There is nitrogen, 14, okay? So we say 14 there. For oxygen, just next to it, 16, okay? So we come back to our calculation. Okay, let's come back to our calculation. We found that for oxygen, for nitrogen, we're talking 14. For oxygen, it's 16, but we don't have just one of the oxygen atoms. We've got two, so it will be 2 into 16. We work this out. This becomes 14 plus 32, all right? And therefore, this is 46 grams per mole. This is the molar mass of what? Of nitrogen dioxide. Okay, so with the molar mass of nitrogen dioxide, we can then find what the mass is, because we know the number of moles. Here is the number of moles, 0.016 moles. Okay, and we use, of course, that formula. Number of moles is given mass over molar mass. 0.016. I think I got that right. Let me be sure. Yes, number of moles is 0.016 equals. Mass is what we are looking for. We have calculated for the molar mass, and the molar mass is 46 grams per mole. Therefore, your mass is 0.016 times 46. So, all right. So we can go back to the calculator here and work it out. Okay, so we can actually, because this is the number of moles, we can just multiply that by 46 and we get exactly what the answer is. So here we've got 0.72 grams, 0.72 grams. So the mass is 0.72 grams, 0.72 grams. So there is that amount of mass in that volume, okay, at standard temperature and pressure, of course. So what is very important here is to see how you alternate between these several equations that you use to calculate for number of moles, and how you use them in such a way that you solve the problems that are being asked from you. So I think you have seen that. Let's move on to the next one. Okay. The next one says 5 grams of potassium hydroxide. So this is potassium hydroxide, KOH, and of course this is a base. Okay, it's a hydroxide. This is dissolved in water to make up a volume of 500 cubic centimeters. Determine the concentration of the solution. Okay, now this should be easier to work out. But then let me just take it slower, quickly, and let me take it slower with you, and then I'm look at how quickly you can work on it without taking the long way. Let's have a look at it. You've got mass given to you. It's 5 grams. You have got the volume that the solution should actually make. It's 500 cubic centimeters. We work in cubic decimeters, so I can actually convert it immediately to cubic decimeters, which is 0.5 cubic decimeters. All right. Okay. So now I have to find concentration. And how do we get concentration? Concentration is the number of moles over volume. So I need to get the number of moles because volume is given to me. The substance is given to me in grams, which is mass. So I need to work out these grams into getting the number of moles. How do I do that? For me to do that, because I've got a substance and a mass of a substance and its molar mass, I can use this formula here. Can use this formula here. All right. Number of moles, it's given mass over molar mass. All right. Now, the molar mass I need to work out. It is a molar mass of potassium hydroxide. Molar mass of potassium hydroxide, what do I have? We go to our periodic table again. For potassium, where it's K, there is K. I've got 39. For oxygen, once again, I've got 16. For hydrogen, there it is. I've got 1. So I can substitute into my molecular formula there and work out what the answer is going to be as being the molar mass of potassium hydroxide. So K is 39 plus oxygen 16 plus hydrogen 1. This is 56. Okay, 56 grams per mole. This is the molar mass of what? Of potassium hydroxide. Okay, so I can then find out what the number of moles is because I'm told or I'm given the mass to be 5 grams here. Okay, there is the mass. So I'll say this is 5 divided by 56 to get the number of moles and work it out from there. Divided by 56, the answer is 0.089. So this is 0.089 moles. Okay. From here, I can then go to the equation or the formula for concentration. Concentration equals number of moles. What's going on here? All right. Number of moles over volume, and that will be equal to number of moles is 0.089 divided by 0.5. That is the volume. Okay, you get to that point, don't worry yourself, you go to the calculator. I should have not erased that. 0.89 divided by 0.5. Okay, I should have just kept it there. Right, that is 1.78. That's going to be 1.78. So 1.78 mole per cubic decimeter. So that becomes the concentration. Okay, there we go. Let me see. I think there's something wrong here. Let me work, because here we made a mistake. That must be 0.089 divided by that. So let's go back to the calculator again quickly. and we fix that. So instead of 0.89, it's 0.089. We divide that by 0.5, and what do we get? We're getting it to be 0.178. So the answer is 0.178. Right, 0.178, 0.178. So that's 0.18, of course, mole per cubic decimeter. So we have found the concentration here, and therefore we have answered this question here. But a quick way of doing it, okay, without following all this, I'm trying to do that so that even those that are struggling can follow it up and get to the end, can find the logic in it. But then another quick way of doing it is to say, if I have got concentration, let me use a different color here. If I've got concentration as number of moles, if I have concentration as number of moles over volume, and yet number of moles in this case is mass over molar mass. If I put these two equations together so that I have C equals this N here, concentration, this N here is the M over M all over volume, okay, if you like. So what you have here finally is M over M divided by volume over 1. So that is, or can be written as M over capital letter M times 1 over volume. Therefore, at the end, you would find yourself having this. Let's work it out. You'll find having C equals M over MV. Right? And therefore, you can quickly substitute there, where you say, okay, that was 5 grams divided by this is 56 times the volume is 0.5. It was 500 cubic centimeters, so it's 0.5. So you can see that should work out to exactly the same answer that we got. Okay, so what you have there, you've got 5 divided by 56 times 0.5. Okay, what do you get? That is, there is your 0.178 or 0.179. Okay, it's actually the same. So this is 0.179. So just because I didn't get all the decimal points together, but you can see that works out to exactly the way it should be. So in other words, once you get used to these things, you can quickly apply that method. Once you have your molar mass and you've got the mass given to you and you are to get the concentration, the volume given to you in that equation or in that question, you can use that formula to work it out quickly. I hope that is helping you a lot. Okay, that's it in terms of the questions that we had here for you to try and look at and see how you can answer them. And of course, we still have our challenge question that is coming, and after this, we're going to look at it, and of course, have some time to also look at your questions as well.
All
Thanks,
right.
Luni.
Mindsetters, don't go away. We'll see you straight after this. Welcome back, Mindsetters. From that break, it's now time for the challenge question. So, TK.
Okay, now let's come to talking about the challenge question that we have here. Remember, you had to work on it. I gave it to you right at the beginning. You had to work on it. It is also a question that takes quite some time for you to work out. But then let's have a look at it. You are asked to prepare this standard solution of hydrogen sodium hydroxide. The concentration has to be 0.75 moles. So concentration has to be 0.75 mole per cubic decimeter. Okay, and then find the mass of the sodium. So the mass of the sodium hydroxide that needs to be used if the volume has to be 200 cubic centimeters. And of course, we can convert that immediately into cubic decimeters, and it works out to be 0.2. All right, now for us to do that, we have concentration, we have volume, we can find the number of moles. Concentration is number of moles over volume. Therefore, 0.75 should be equal to number of moles over 0.2. You work this out, you find that number of moles equals 0.2 times 0.75. Okay, so let's work it out. 0.2 times 0.75. All right, and the answer is 0.15 moles. So we've got 0.15 moles of sodium hydroxide that we are to use. Now, if we've got 0.75 moles of sodium hydroxide to use, okay, what will be the mass? Now, for us to get to the mass, we now also have to find the molar mass of sodium hydroxide. Okay, molar mass, sodium hydroxide. How do we get that? Remember what we do. For sodium, you go to the periodic table. It's 23. Okay. I know it's 23. So sodium, where is it? There it's sodium. 23. Oxygen we found the other time, it's 16. Hydroxide, hydrogen is 1. So we go back to our calculation and say 23 there plus 16 for oxygen plus 1 for hydrogen. Okay, so we've got 3940 grams per mole. Why do we do this? So that we can find the mass that they are looking for, because the number of moles is given by given mass divided by molar mass. Okay, and because we know the number of moles that we have calculated here, okay, we found what the number of moles is there. We can then substitute here and say this is now 0.15 moles would be equal to the mass that we're looking for divided by the molar mass, which is 40 grams per mole. Okay, therefore your mass is equal to 0.15 times 40. So you come here, I already have my 0.5, just multiply that by 40 and I get the mass. That works out exactly to 6 grams. Okay, so I need 6 grams of sodium hydroxide to prepare that standard solution of sodium hydroxide in a volume of 200 cubic centimeters. So that's what I needed to do there. So quickly you could see you can actually find the mass there. Now we want to dedicate this time to the questions, and I think we do have a few questions that you have asked there.
Yes.
The first one?
It's from Sanel Mtambo.
Okay.
How do we write given molecules or combined elements in symbols?
How do we write given?
Molecules
Yeah.
or combined elements in
Yeah,
symbols.
and symbols. Okay, let me try to make sense of what you're saying with the combined molecules and symbols. Let me look at this one here. Say I've got ammonium sulfate, and the formula will be like that. And some people would be asking, but why is the formula like that? Look at that. We say you've got the SO4 2 minus there, and you've got the NH4 plus. It's a 1 plus. We just don't write it there. When you put these two things together, the quickest way to get this is to say this one, without a charge, it's going to be a subscript there. And that one without a charge, it's going to be a subscript there. That's how you find your molecular formulas. Okay, so that therefore means you end up with the NH4. Because this is together is one thing, I can't just put the 2 here. So I need to say for all this, these 2 is there. And then SO4, for all of it, this 1 is there. But because 1, I mean, 1 multiplied by any other number, it's that number. Okay, so it won't change anything there. So if I have it like that, for example, and I am to calculate, say I want to find the molar mass of NH4 to SO4. What am I going to do? In the same way, we went, I think we found for what for what nitrogen is. And I'm using capital brackets here because I've got other things coming inside there. I've got 14 for nitrogen. I've got 4 for hydrogen, which is 1. But for all of them, I've got to multiply them by these 2 here. Get it? So you have to multiply by that because this 2 influences everything inside that brackets. Okay? Then I would say plus. Now, plus for sulfur, you go to your periodic table and look for sulfur, where it's sulfur. Sulfur is a nonmetal, so we should look for it that side. You can see it is 32. Okay? So 32, it means I come back here. Okay, say this is plus. Okay. Plus 32 for sulfur, plus for oxygen, I've got a 4 times 16. Okay, for oxygen there. Then I would work this out. I can actually get what the answer is. All right, and 14 plus 4 is 18. 18 times 2 is 36. 36 plus 32 is 68. So 36 plus 32 is 68 plus 14 times 16. Let's just quickly get that one. 14. Let's put that there. So, I mean, not 14, but 4 times 16. Okay? 4 times 16. What will that be, right? What will that be? It's 64. So you add 64 there, and then you get what that is going to be. So 64 plus 68, that is going to be 2. Carry 2, 6, 6. 12 plus 1, it's 13. So that will be 132 grams per mole. Okay, that will be the molar mass of that. So I believe that helps you to see when you have got this myriad of atoms together, polyatomic molecules, okay, or polyatomic ions in a particular substance, you see how to work it out. You have to make sure that that subscript that influences everything inside the bracket is used accordingly and correctly. All right.
All right, thanks, TK. And then this is from Nico Sibuyane. How to calculate the volume when you are given the mass of the substance in STP?
The mass of the volume when you're given the mass of the substance.
How do you calculate the volume when
The
you are
volume.
given the mass of the
Okay.
substance?
So you're calculating the volume when you are given the mass. You calculate the volume. Sorry, mass is given to you. Okay. Mass is given to you. Now you know that we're talking about at standard temperature and pressure. Oh, we. Okay. Standard temperature and pressure. So we're talking at STP. At STP, this formula is what we have. It has got nothing to do with mass, but everything to do with volume. So given volume over the molar volume, which is 22,4 cubic decimeter per mole. Okay, so now, if you have it like that, you don't have mass there. Mass is not given to you. So you would then need to work out this mass in terms of the number of moles. So if it's a gas, say a gas of, say, carbon dioxide, just giving an example, it means that you'll need to work out the molar mass of carbon dioxide, which will be, so for carbon, there we go, we've got a 12. Oxygen, we know it's 16 there. So let's see. It means you would have 12 plus should have written this first here. So it means this would be equal to 12 plus 2 into 16. So that is 32 plus 12 is 44 grams per mole. Okay? So from here, you are therefore going to use this formula. Going to use the formula that says number of moles is mass over molar mass. In this case, when you do that, you get the number of moles. Okay? Which where your M there will be substituted by that if the gas is carbon dioxide in this example. So when you do that, you now have number of moles from the given mass. If you have that, then you take the number of moles, you substitute into that formula, and therefore work it out and say, okay, substituting into that formula would mean that the volume, which is what you are looking for, will be equal to number of moles times the molar volume, which of course we can put there immediately because we know it. Okay? We know that the molar volume is 22.4. All right? But then that N here, that N you would have found by using that formula. You substitute there, you get what the volume is. So you can work backwards, you can work back to front with these things. You can start from the back, front, backwards, as long as you find the logic in it. Okay? We have got number of moles equals to volumes over molar volume. We have got number of moles equals to given mass over molar mass. Okay? We've got number of moles equals to concentration times volume. So all this you can put together in a logical thinking, logical sequence, and be able to answer so many questions based on this.
All
Any
right.
other one?
Thank you, TK. From Sanele again, how do you tell if something is acid or base?
Oh, Sanele.
Yes.
Okay. Acid or base? If you go back to grade, is it grade 7? I think 5, 6, 7 down there where you say acids have got a sour taste, bases have got bitter taste and all those things, but we don't want to taste them, right? But all the time, when you have substances with a hydroxide, Sanele, if you have got a hydroxide, by hydroxide we mean the OH minus, like we had sodium hydroxide, we had potassium hydroxide, all these, because of that hydroxide of this thing, they are bases. Okay? Right. And then acids, okay, usually you've got your very soluble or very strong acids. I think you would know them. The hydrogen chloride dissolved in water gives you hydrochloric acid. Okay, so this will be your acids, your nitric acids, your sulfuric acid. Okay, right. Now, what is characteristic of the acids? I will show you right now. You can also have all sorts of other acids. Now, look at it here with the acids. That hydrogen has got a very, very important role to play in that substance for it to be an acid. And for that reason, when you deal with acids and bases, we do have theories that says acids will be all substances that donate hydrogen ions, or what we call protons. Okay? And here bases will be all substances that accept or receives protons, or the hydrogen ions, protons. Okay, so those will be bases. Okay, fine. So I think up to that point, you would have understood what a base is. There's more to it. You will learn more about it, I believe, when you get to grade 12 as well.
All right. Thank you, TK, so much for the lesson. Mindsetters, thank you so much for tuning in. Until next time, I'll see you then. Same time, same place. But from us, goodbye.
Bye-bye. Thank you for watching.